first of all, okay. So, I really thank you very much for giving me the pleasure to present this few results and research lines in front of you. I have a long title, and I want to talk about partial differential equations, which are equations that are used extensively in physics, biology, mathematics. And these solutions to these equations, one would like to know what they do, what are their properties. And I will, yes, it's working. I will present two examples of results. For example, one very recent, which is that of stability for solitons of nonlinear Schrodinger equation. And another example, which is singularity formation for models coming from biology, bacterial motion. Okay, so here's the outline of the presentation. So first, I will do an introduction, like Flora really made sure that explain all the basic stuff. So I try to do my best in explaining the basic stuff. This evolution equation, and what are the subjects that I want to really do my talk about somehow, this solitons of self-similar solutions. And then, as I said, I will just illustrate with two examples. The first example will be explaining how we can have propagation through space due to specific solutions, which are these solitons and self-similar solutions for the nonlinear Schrodinger equation. And then the second example will be how we can have concentration state of density of bacteria for another model, which is the Patak-Keller-Zegel model of chemotaxis. All right. So, part one, what are these solitons? Self-similar solutions. I will use it as a synonym. It's just that we use these words in, first, I guess that first soliton had a very precise meaning, but now it's used everywhere. And so I prefer just to say that these are self-similar solutions, but in the field we call them solitons because it's short. Okay, but so for me it's going to be the same. You have to, I won't go too much into details, but you have to imagine that a partial differential equation is an equation for some function. But here I will look at particular ones, which are evolution partial differential equations. So somehow these are abstract mathematical equations, which give you the time evolution of a system. And so you have the so-called initial state, which I will denote by U0. And then this equation will just tell you how this should evolve with. So you have initial data, then something evolves with time. And what you want to understand is, okay, what will happen? The system evolves. And so, in fact, two things can happen. Either the solution will live for all times, very, very long times, and then you want to know for very, very large time what will you eventually see. Or maybe this is some specific mathematical phenomenon, but this can happen and can have also physical and biological meaning, as I will explain. Maybe this solution will not be able to live for all time. Maybe at a given time, something very spectacular will happen, and the solution will become what we call singular. And then we also want to know what is happening, what is preventing the solution for existing for all times. And so this has been a very active topic within the field. So it's really a mathematics. Give me an abstract model, an abstract equation, and then we try to prove theorems about what the solutions do. And basically, since this is partial differential equations, we have a function defined on the continuum. There are two kinds of phenomena you would like to study. First phenomena is just propagation, so your function is moving, propagation through space. Second phenomenon is concentration through scale. Maybe you have a function that it concentrates to smaller and smaller scale, or maybe to larger and larger scales. And what I want to emphasize in this talk is the role that very specific solutions of this equation play, which are called these soliton solutions. Okay, so what to expect? So here is, I think, a funny video, which is the one of the Zabriskie and Kruskal numerical experiment. So somehow it builds on a previous experiment of Fermi, Pasta-Ulam, and Singer. So what are these experiments? This is the first numerical experiment ever. Okay. 1953. It was done in Los Alamos, and well, they were. Okay, I'm not gonna go into detail, but after this, they found something a bit strange in their numerical simulation. And then later on, Zabriskie and Kruskal did a numerical experiment for a closely related model, and they found out that something quite particular was happening. So let's look. So I think that what is funny is that this numerical experiment is in 1955. So you can find it. You can find it on YouTube, and so actually at that time they could not record the numerical simulation, so they were displaying the result on the screen of a computer and filming what was happening. Okay, so I'm really happy to find this numerical simulation on the internet. And so okay, here it was going a bit fast. So go from the beginning. Okay, Zabriskie and Kruskal. So this is an equation. You don't need to know what the equation is, but just here, this is the initial data. And what you see is that, okay, first, just a shape like that. And then let's see what happens. So you see these things forming, right? And they move from left to right. Okay, you have a similar thing here. And so these shapes, they have appeared. Okay, they were not here initially, but then they appear and they seem to be quite stable and they seem to propagate through space, which was one of the things I wanted to emphasize. We want to study. And in fact, so this is an equation which just models water in a channel. So you can just have this in the Garonne, I believe, in France. So you just have a very, very thin river. And at some point, you have what we call mascara in French. Maybe. So you will see just some waves in the channel. And this equation was derived for such wave in the channel. And so, in fact, this numerical experiment, what it is telling you is just the following fact, is that you put water in your channel initially, then you make the water evolve according to my equation. So it's not mine, it's the equation. And then if you wait long enough, what you see is just a wave that goes in front, with behind another wave, and with behind another wave. Okay? So you start with some random water in your channel, but eventually what you will see are just waves that propagate and keep the same shape. And it was very influential, these numerical experiments in the field. And so what we see is that particular solutions emerge and that they are responsible for something which is what you would expect, is that you have a wave equation. The wave equation produces waves propagating. Okay. So, well, of course, this is just a numerical experiment, so it's not a math so far. And what you would want to prove are actually rigorous results, because we are mathematicians. So what we want to prove are actually rigorous properties for these equations, and to prove rigorously that the solutions of the equation has something to do with these solitons that we see. And there have been numerous works on that over maybe the past 20 to 25 years. So the big meeting in mathematics is the International Congress of Mathematicians. This is at this moment that the Fields Medal is given. And if you are a speaker at the International Congress of Mathematicians, it's really a recognition of your work. So this is what is trendy, say, in the field. And so here you can see I listed some of the speakers whose work that they were discussing at the International Congress of Mathematicians was about the role of these particular solutions in partial differential equations. And as you can see, it's really bigger and bigger. So right now, within the field of partial differential equations, trying to study what these specific solutions have to do with the equation is really a trend. Okay. All right. So yes. What do you want to do mathematically? You can try to prove several types of results. So if you believe that I give you the initial system, then it evolves with time. And then if you wait long enough, you should see these particular solutions, the wave that we have seen. Then you can try to prove several types of results. There are several directions of investigation. The first one is just, well, what are these particular solutions? Are there these solitons, these self-similar solutions? Can you find them? Can you study their properties? And then, can you prove actually what I was saying, that if you start with any initial data, if you wait long enough, you will just see this soliton, see this. And once you have this in mind, that any solution should actually involve these solitons, you can try to maybe construct relevant examples. So you take your equation and you show that there are some very specific solutions which, because of these particular solutions, will have relevant phenomena. So for example, just wave propagation, okay? Something propagating through space. Here I wanted to illustrate, for example, what we can do in the example of the nonlinear Schrodinger equation in 1D. So this is a recent result I obtained with a collaborator. So this, okay, is a famous equation. It's called the Schrodinger equation. And since here it's u to the cube somehow, we call it the cubic nonlinear Schrodinger equation. And here is typically a wave of this equation. I mean, when you look at it in a particular set of coordinates, it's just a wave that is propagating. Okay, so it's really as the numerical simulation I showed you. This equation too, it has particular waves which just translate in space. And so here I will not go into details, but this equation, it has a very strong property which is called integrability. So somehow there is a way to, a complicated way, but there is a way to compute the solutions and to show that with this computation at hand, what you will see at later times are actually waves which are propagating in different directions. So this was found for this integrability by, for example, the work of Zakars and Chabat that I quote here in 72, and there are results and still nowadays on that. So here, okay, the reference you cannot see. I put the reference where they actually show that rigorously. Okay, but so this equation is very particular because it's integrable, and well, so here is just something very mathematics, but life is not always integrable. So you want also maybe to study an equation which is not integrable. And so here, okay, before there was a cube, so why not adding a quintic nonlinearity? Then you end up with another equation. So this is really an evolution of partial differential equation. And you would want to study all the types of questions that I have raised before. But since it's not integrable, in fact, mathematicians cannot really say much. We cannot say, actually, for this equation, that these waves will appear for a long time. But maybe we can ask, say, smaller questions, like, are there actually these particular waves which are traveling? And, okay, so here, okay, I don't want you to be too much afraid of the notation, but rather to listen to what I'm saying. What I'm saying here is that there are such traveling waves for this model. Actually, it's given by an explicit formula. So, okay, I will present the graph soon. But you have these particular waves, which are called ground states. And so, for example, here I quote a result which applies, but I mean, since you have a formula, you can check directly, but there is a general theory, for example, developed by Beresticki, who is the PhD advisor of the PhD advisor of my PhD advisor, and Pierre Williams, who is like a famous field medalist at France. And okay, there is a way to find this particular traveling waves. And for those of you who do physics or math, they are intimately related to what we call the symmetries of the equation. So here you have symmetries, and they naturally are associated with self-similar solutions. Here's the function. Okay, it's just a L function. And the thing is that this is a traveling wave. So here I just plug it at a given time, but you have to imagine that this is moving to the left at constant speed. Okay, so it's really a wave that is propagating. And well, we have found traveling wave, but what are its properties? And maybe the first property you would want to study is just if you want that this object plays a role in the dynamics, it should be somehow stable. If you perturb it, the wave should not collapse and disappear. Because if these objects are unstable, you would not see them in real life. Okay? So maybe the first thing to investigate is whether they are stable or not, because if they are stable, then you have a chance to see them in real life. And the first notion of stability that has appeared is that of orbital stability. So here we are in the East Coast, Grillakis, Chatham-Strauss of the United States. There was also another important line of work done by Cazenave and Lyons and collaborators. And the result is the following. So, okay, if you're not familiar with mathematical notation, just listen to what I'm saying. The thing is that if you start with an initial state which is very close to this wave, okay, so we had a wave propagating, we just perturb it a little bit, and then such result says that you will retain the shape of a wave. Okay, so you will be equal to a wave. So this is a wave, like this solitary wave, plus something, and this something is small. When you see epsilon for mathematicians, it's that is small. Okay, this is our number to say that there is something is very small. And so for the physicist, this has to do somehow with the fact that this is the ground state of the equation. Somehow it minimizes the energy at a given mass. And with all these techniques, what you can prove is that since this is due to this energy and mass constraint, you have to be close to the ground state for it. But the thing is that the ground state, since your equation is invariant by spatial translation, you don't know where that ground state is. And so what is missing with such theorem is what is the position of your wave.
Explain for expressing is what's the ground state? It's a state of a system with a minimum energy, because what is not the ground state is not.
Yeah, so I will repeat what you say. The ground state is the state of a system with minimal energy.
Yeah, okay.
And so somehow it's what is expected to be the stable configuration of the system. Okay, and so here is the first notion of stability, which tells you that you have to look like a wave, but you don't know actually where is your wave. So you don't really understand wave propagation. And so this is the type of result that I obtained, like, for example, this year with my collaborator, which is a refined version of that. So somehow I start with the same thing, is that I study this equation, I have my wave, which propagates, I perturb it a little bit, and then what I can say is that my solution will look like a wave plus some little perturbation, but the wave will actually converge to some fixed wave that propagates at speed infinity. Okay, this is okay. What is displayed here? It's that my soliton will reach a final value, will reach a final state of the system. And so this is really the fact that these solitons, these waves which are very particular solitons, very particular solution, they are very stable. I perturb them a little bit, then the perturbation goes away, it goes to infinity. This is what is said here. So the perturbation really, you don't see it for later times, and you will only converge back to some very, to the same traveling waves as before. And so here, I should mention a little bit of bibliography. It's going to be online, so I should quote who has worked on that before. So we have, for example, the first important work, which is that of Buslaeff and Germain, then Buslaeff-Sulem. Maybe very influential to what we have done here is the work of Krieger and Schlag. And also there is a work of Martel that I should mention, where he actually showed this result for this equation, but with completely different techniques.
She was in Cergy.
Martel was in Cergy, that's true, I should mention that. No, Yvon Martel was in Cergy, so he's now in Versailles, not too far away. And actually, so he could show a result which is similar to that, but not exactly the same, actually, and with different techniques. So, okay, just to say that right now there is an intensive work on that. And the reason why this wasn't proved before is because actually there are some additional effects we would want to study, which is the fact that the remainder, it just does not go away and just remain very small and linear. There is an additional effect that you have to study, which is called non-range scattering, which is the mathematical difficulty. And so, okay, mathematicians will like to do proof, but I knew that proofs would be too much for you. So I'm just going to do the concepts. What you want to understand when you want to prove a rigorous result like that, I just want to emphasize what is going on. The thing which is going on is that your system is written as the wave, which is your soliton, plus the perturbations. You have an extra, I mean, it's not exactly a perfect wave, you have a perturbation. And then what you want to understand is how you are seeing them somehow as two particles interacting. There's really a particle-like structure. Then you have some reminder. And you want to understand how the two will interact. So the fact that you have a big wave, it will actually impact a lot how the small waves will propagate near the big wave. So this you want to understand. And these little waves, you want to understand how they escape to infinity, how they remain very small. And the problem in this type of analysis is that the small waves, they actually also contribute to the big wave, and they go somehow also to make the big wave even bigger or even smaller. And you have to understand that. Maybe the big wave loses energy, or maybe it gains energy, and you want to understand. Finally, the little waves, they have some self-interaction that you have to understand, which is causing what we call a long-range scattering. And so you see, here I'm not giving any particular details, but what I want you to understand is that somehow we have this picture in mind of the solution being made of several components which are interacting together, and you want to have mathematical tools to describe these interactions and to describe this phenomenon. I won't say more than that. And so, okay, this was the first example. This example, so let me sum up what I did. There was this equation, which was a wave equation, and we wanted to understand how waves propagate. And there were particular solutions, which are traveling wave solutions, and we wanted to know if they were stable or not, which is the first thing that you want to understand if you want to prove that any solution should actually look like that. The other phenomenon that I wanted to describe today was that of concentration. We've seen propagation through space. So what about concentration? And in fact, we will now have a look at a completely different equation, which comes from a completely different background. But what I want you to feel is that since we are doing mathematics, in fact, we don't really, okay, of course, we care about the physical motivation, but we care about somehow universality. And an equation which arises to describe waves can have similar properties as an equation which arises to describe bacteria, for example. Okay? Mathematically, it can have similar properties. So here is a model proposed by Patlak, Keller, and Zegel. So, okay, this is, you see, there is a partial derivative. So it's still an evolution partial differential equation. It's still an equation which describes something that is changing with time. What is changing with time? It's just a density of bacteria. So bacteria, they move. And in fact, with this model, they release chemicals in the environment. The chemicals spread, and then you have this thick law of diffusion here. And then where you have the highest number of bacteria, you have the most concentrated chemical there. And bacteria, they sense that there is more chemical component over there. And so they will move toward where there is more of this chemical substance in the environment. This is how they detect where the other bacteria are located. And also, since there is some randomness in their motion, then you have also some diffusion. And so here is like a true experiment where you have Escherichia coli. This is, so you can see the light displays where it is. And so there is a particular phenomenon is that you can see that, okay, they seem to move and to be attracted to some particular locations in space. Okay, they detect where the other bacteria are, and in the end, they all go to the same. So how do you see that mathematically? So here's a numerical simulation done by a collaborator of mine. Again, one. So I will start with an initial distribution of bacteria. This is the density. Okay. So, and you can see that it's spread. Okay. Bacteria are not at a given location, they are a bit everywhere. And when you see bright colors, this means that there is a larger density. So here there are slightly more bacteria than in the other locations. And so what will happen is that, well, bacteria will all move, and you see they move here, and boom, the density goes to plus infinity. This is a very striking phenomenon. I will put again this numerical simulation, that you start with just a given density, bacteria are a bit everywhere, and in finite time, all the bacteria, I mean, at least a large number of them, they all went to the same point. Okay? And of course, well, this is related to the picture that I showed before, where it seemed that Escherichia coli was really attracted to a point. So of course, this is the first order modeling, so bacteria do not actually go to the same point. Something else happens before that, but it's a first order approximation of the phenomenon. Okay? And this is called a finite time singularity formation. And in fact, it can be understood a bit similarly as we understood before wave propagation. So to understand wave propagation, we first wonder what were these very specific solutions which are just these waves that propagate, exact waves. So here, what is the analog? So again, as I mentioned for people doing physics or mathematics, it's related to the invariances of the equation. So you can check what are these invariances, and there is the so-called scaling invariance, that things which are happening at a smaller scale in space are actually the same as things happening at a larger scale, but they just happen much faster. And of course, the prime is invariant by spatial translation. So these particular solitons here are stationary states, which are states for which nothing moves. Okay? If I put bacteria in this particular, so here you can see there is a plot of these stationary states. So if my bacteria density follows the green line here, I am at equilibrium. Bacteria, they want to move because they go randomly in their environment. At the same time, they are attracted by the other bacteria. And if you sum these two effects, they exactly balance. So this is stationary solution, this here. But due to the fact that I have some scaling symmetry, I can find such stationary distribution at any given spatial scale. So I can have one at spatial scale 1, which is the one in blue. But I can also have a stationary distribution at spatial scale 1/2, or even 0.75, or even at spatial scale 0.5. And so actually, the stationary states will produce the video that I was showing here. Okay, that. So I put to you the video again. Here. So actually, it's not a mathematical theorem. It's rather a conjecture. But here, what you will see here, if you were able to zoom on what was happening near this point, what you would see would be this coherent structure. And so this is a theorem that we have obtained, for example, with my collaborators. It's that there exists a solution which looks like exactly these particular states at which the dynamics are steady. But in fact, the typical scale at which your solution is will go to 0 in finite time. So here is an ugly formula, but just wanted to show it because, okay, sometimes things are a bit weird in mathematics. So it's like a parabolic scale for those who are familiar with parabolic scales, but you have some modification to it. And this is an example of a solution that I showed in the video. So this is a mathematical theorem which says that for this equation, there exists a solution which shows that bacteria all move to the same point, that the bacterial density goes to +∞ at just one point, but it actually tells you that if you were to zoom near this point, where something very particular is happening, then you would see what I was calling a soliton. You would not see something very weird, you would see something very coherent happening. So I have to mention the previous result. So to my knowledge, this is the first example of, we'll come that in the next slide, but what we call singularities of the second kind that was actually studied rigorously mathematically. And for that, Velasquez was invited to talk at this International Congress of Mathematicians that I mentioned. So it was in the list at the beginning. And then here, okay, you can see another person who has worked on that is actually my PhD advisor. All right. So what I wanted to say now, this is a bit more specialized, more of these mathematicians, but it's that we have seen two types of such similarities, in fact, in these two examples. The first one was the one describing propagations through space. And this is what we call self-similarity of the first kind, because the shape that your solution will take and the parameters of the motion, they are universal. They can be found from dimensional analysis, while for the second one, the exact scale at which the solution was concentrated had a very particular formula. And this is called self-similarity of the second kind. The thing is that you cannot guess at which scale your solution will be. It will not be universal. This scale will actually depend on the solution itself, and you have to solve a spectral problem in this case to determine at which scale it could be. And so here are some work of, I mean, so for example, Baron-Blatt was very influential into bringing this concept of self-similarity following Zeldovich and differentiating different types of self-similarities. So there's a very nice book. Okay, so I guess time has come for me to finish this presentation. So I was telling you about evolution partial differential equations, which are mathematical equations for which you specify the initial state of your system and which give you how it evolves. And we wanted to understand what happens for later time, either for very, very long time, or when you have this singularity. So if you didn't know what the singularity was before, it's really the second video we have found where something goes to plus infinity infinite time and it's very weird. What I was trying to convince you is that if you want to understand that, if you want to understand what is happening, then you have to understand very particular solutions, which are what I call these solitons or self-similar solutions. And these solutions, they keep the same shape, but they just either move at different locations or move at different scales. And thinking as somehow ordinary differential equations, you should think that they are the attractors of the dynamics. Solutions are attracted towards these specific solutions. And right now, there are many people actually working on solutions which, in the sense that I just gave, can be called as working on their stability and the role they play in the dynamics. And as mathematicians, we are interested in these 4 questions, really, like, do such very particular solutions exist? And if so, what are their properties? Then, if they want to, if they were to be meaningful physically, this would be because they are somewhat stable. So this is how you can expect to see them in real life, because if you perturb them a little bit, they should actually remain there. And they are responsible for very particular behavior. So here, let me go back to the second example I gave. I was telling you that there were distributions of bacteria density which were at equilibrium. If you're at equilibrium, then nothing happens. Okay? But in fact, this equilibrium states generate thermodynamics. Is this singularity formation where all bacteria collapse to the same point. And so it's another interesting question mathematically is that, okay, once you have these solitons, actually, if you excite them in a certain way, if you make them interact, maybe they will produce some interesting. A very final goal that one would want to prove is actually the first one I mentioned with the first video I showed. You remember there was this waves in a channel, and if you waited long enough, you were just seeing a wave in front, followed by another wave, followed by another wave. And actually, one would really want to prove that mathematically. Like if you start with anything, and if you wait long enough, then maybe you are just seeing these self-similar solutions, but something little waves. And so I hope that I could explain to you a little bit of what was happening in this example of propagation in the 1D channel for the nonlinear Schrodinger equation, a little bit of how you could also understand concentration at various spatial scales for this model of bacteria motion. And I hope that I could convince you a little bit that there is some mathematical universality here. In that actually, these 2 points, they seem to be very, very distinct at first. But if you go down to the mathematics and if you study really the equations, then there are some striking similar features. And you can try to have the same mathematical approach to study this phenomenon. I think that one understands well a field if one gives the open parameters in the field. So for example, for the equation that I showed you, this Schrodinger equation with cubic kinetic nonlinearity, it's actually a completely open problem to show that if you start from anything and you wait long enough, you will just see a wave followed by another wave, followed by another wave. For the moment, it's completely open. Mathematicians just don't know how to do that. So this is very specific. So here it's just for mathematicians in the audience. So actually, the result that I mentioned, it showed like a stability for some wave in 1D, but there was no resonance, no internal modes. And actually, if one would want to study what happens when you have these particular things which prevent some good decay at the linear level, okay, like the parenthesis. And then, in fact, I showed you an example of a very particular dynamics in which all bacteria were colliding at a single point. But, okay, this is one particular example of singularity. In fact, there can be plenty of other ones. And for the moment, it's still unknown what happens generically. So what should happen? So there are two things that what one would want to do is to give further example of singular solutions. Okay. Are there even more particular singular patterns for solutions? Can you find other ways to make all the bacteria collapse to the same point? And then at some point, you would also want to classify what is happening. So here I showed you a very particular example, but so maybe we can hope that there are other examples to find. But at some point, we would like to say that the particular examples that we have found are the unbiased, which means that we have understood everything. And of course, here I was presenting you two equations which are somehow very particular. One coming, so this nonlinear Schrodinger equation, and another equation which is what we call a parabolic reaction diffusion equation. But you would want to investigate what is happening for other classes of equations, because these phenomena you would expect to see them in fluid mechanics, in other wave equations, etc. And so this was what I was mentioning. I was granted a fund by the ERC for a starting point project. The acronym is FLOWS for flows, waves, and asymptotic stability, and it's gonna start soon, next January. And so these are the type of studies that I would want to do and problems that I would want to address with this point. Okay, so I thank you for your attention.